Hi guys, and welcome to my first AP Chem review. So in this series of videos, I'll be going over topics from the Chemistry for the AP test. Currently it's April 16th, and the test is about a month away, and this year it's online. So I'm going to try to make a video every single day with a new review topic. So like I said, every day I'm going to do a new topic. But in the few days before the AP test, I'll do general review, do some general FRQs, because that's all that's on the test this year. But up until then, I'm going to be doing topic by topic review about all the different standards that they will be testing on, not only the 2020 test, but what they tested on the 2019 and what they will test for 2021 for anyone that's viewing in past years from the 2020 test, because I know they cut out some of the material this year. But if people are watching this later, they're not going to be limited to just what's being tested this year. So let's get right into the video. So for this first AP Chem review, we're going to be talking about periodic trends. This is probably something you definitely learned early on in chemistry, and you most likely forgot it. So to kind of review, what are they and what can we use them for? So to answer the first question, what are they? Periodic trends are trends in data that we see as we move up or down or across the periodic table. So, for example, if we're looking at atomic radius, we can use our knowledge of the periodic table to determine what elements will have a bigger atomic radius or a smaller atomic radius based off of where they are on the periodic table. And that kind of leads me into my second question is, what can we really use them for? So with these, we can determine the traits of elements relatively compared to other elements of atomic radius, first ionization energy, and also Coulombic attraction. So that's kind of what periodic trends are. Let's get into a couple review questions. All right. So in this first question, it says, circle the atom with the larger atomic radius. So with these type of questions, when you get a set of elements, in this case it's just two, you need to really look at where they are in the periodic table. So the first is aluminum and boron. So we go to our periodic table right here, and we find aluminum and boron, which are right here, element 5 and element 13. So they're in the same they're in the same row. No, they're in the same column, but a different row. So that means the number of valence electrons isn't any different, but what is the number of electron rings, because we know as we go down the rows, you add an electron ring every time. So boron has 2 electron rings because it's in the second row, and aluminum has 3 electron rings. And simply because of that reason, we know that aluminum will have a bigger atomic radius because it has more electron rings. So the next question says phosphorus or chlorine. So like the first one, we need to look at the periodic table and locate those two elements. So phosphorus, which is right here, and chlorine, which is right here. So in this case, they're in the same row, but they're in a different column. Phosphorus is element 15 and chlorine is element 17. So we know that they both have 3 electron rings, so that can't be the reason why the atomic radiuses differ. But what does differ is the number of protons. So in chlorine there are 17 protons, but in phosphorus there are only 15. And this is going to lead to the reason why the atomic radiuses differ. So electrons are negatively charged, and they're on the outside of an atom, and protons are positively charged on the inside. And we know that positives and negatives attract. So because of this reason, we know if there's more protons to pull in the electrons, it's going to pull them in closer and closer, making the atomic radius different. So think about it this way. We know that chlorine has more protons, right? So there's 17 protons for chlorine and 15 for phosphorus. So if you have chlorine right here with 17 and phosphorus right here with 15, the chlorine is going to pull the electron. These are both electrons. It's going to pull on the electron stronger than the phosphorus is. So because of this, the electron will be closer, and it will make the atomic radius smaller. And for this reason, we know that the larger atomic radius will be the phosphorus. And it's because there are less protons to pull in the electrons. So basically, to recap this, about the periodic trends of atomic radius, we know as we go down the periodic table, the atomic radius increases because of the number of electron rings. And the atomic radius also increases as we go to the left because of the number of protons. So that's the periodic trends with atomic radius, but let's get into some other ones. For our next set of periodic trends, we're going to be looking at periodic trends with electronegativity and ionization energy. And while these two terms are very similar and they do follow the same periodic trends, first we should kind of look at how they differ so you kind of understand what they are when we're going through the periodic trends. So you probably learned this earlier in chem as well, and you might have forgot, but electronegativity is the strength to pull electrons within a bond. And ionization energy is the energy or the strength to rip off an electron from another molecule. So I'll kind of draw this for you. So like if we had H2O, the electronegativity of oxygen would represent how strong it is pulling on the electrons associated in the bond right here, in those two bonds. But ionization energy is, let's say there's an atom of fluorine right here, and then there's an atom of barium right there. Ionization energy is the energy that the fluorine exerts onto the electrons of the barium to pull away one of its electrons and bring it to the fluorine. So that kind of shows you what electronegativity and ionization energy are. And they're going to be going through the same periodic trends, but it's just nice to know what they are and how they differ. So in our next set of questions, we have an electronegativity question and an ionization energy question. But to be real, these questions, you figure them out the same way. Ionization energy and electronegativity in the sense of periodic trends are essentially the same thing. And I'll show you why. So first, let's get into the first one. So which has a higher En or electronegativity, germanium or copper? As with any periodic trend, you need to look at the periodic table unless you have it memorized. So you look on here and you have to find germanium and copper. So you find germanium here as 32 and copper here. So they're in the same row but a different column. And as with the other ones, with that we know that the difference is only in protons. So germanium, because it's element 31, has 31 protons, and copper is 29, so it has 29 protons. So, which means how much of a pull it's going to have on electrons, because positive and negatives attract. So, first, to answer this question, we need to kind of understand what electronegativity is, and I kind of went into that before. But electronegativity is how much an element pulls on another element from a different molecule in a bond. So because germanium has more protons, it's going to pull more on electrons. So from that, we know that germanium will have the higher electronegativity. So to kind of explain that again, the reason why germanium has a higher electronegativity is because it has more protons, which then means it pulls on the electrons of other elements stronger than the copper does, because positives and negatives. So for the next one, it says, which has a higher ionization energy, lithium or potassium? So as with every other single one in periodic trends, you must look at the periodic table first. So lithium is here, right there, and potassium is there. So they're in the same row, same column, but a different row, which means that their electron rings are different, and that's what I've drawn out right here. So lithium has 2 electron rings, as seen in the diagram, and potassium has 4. So this is going to play a big key into the difference in ionization energy. So, because of the electron rings, obviously potassium is way bigger than lithium. It has a way bigger electron cloud. So the answer to this question is lithium, and I'll kind of explain why. Because it's kind of hard to explain, But even though potassium is technically pulling on electrons from other atoms more strongly than lithium because it has more protons, its electron cloud is so big that it kind of negates the effect of the pulling because it has to pull over such a long distance, and the charge gets negated because it's pulling over such a big area. With lithium, though, it's so much smaller than potassium, and even though it has less protons, which technically means it's pulling less, it's pulling over a way smaller distance, so it can pull a lot more stronger. So as I did with atomic radius, I'm going to kind of summarize up ionization energy and electronegativity with periodic trends. So for both of them, they go with the same trends, and that is they increase as you go from left to right because of the number of protons, and the more protons mean you're pulling more on electrons. And as you go down the periodic table, your ionization energy and electronegativity decrease because you have to pull over a greater distance than the elements higher above because of the amount of electron rings. As said earlier, ionization energy and electronegativity aren't the same thing, but they both deal with the same. They're both very similar. They both deal with pulling electrons. Electronegativity is just pulling electrons within a bond, and ionization energy is just about pulling electrons from a different molecule that isn't bonded to. So there you go. That's periodic trends. Hopefully from this video you learned how to compare elements, ionization energy, electronegativity, and atomic radius using the periodic table. If you have any questions, please comment, and be sure to tune into my future AP Chem Review videos coming shortly. Thanks for watching AP Chem Review, Lesson 1.